Hey guys, my name is Scott from Chegg Tutors. I typically tutor subjects like chemistry, biology, statistics, psychology, and sociology. And today we're going to be going over a chemistry topic. Now, if you've seen my other video, you'll know that I did a previous video in terms of dipole-dipole interactions. Today, and for this video tutorial, I'm actually going to be going over London Dispersion Forces. Now, London Dispersion Forces is another form of intermolecular bonding or an intermolecular force, okay? Likewise, hydrogen bonding, which is in another video tutorial, is another example of intermolecular forces, okay? So, in terms of London dispersion forces occurs between molecules, just as dipole-dipole interaction, just as hydrogen bonding. And let's review a little bit briefly in terms of what exactly is an intermolecular force. Now, intermolecular force is an interaction between molecules, okay, between two or more molecules. And this interaction, based off of what type of molecules they are, would result in a hydrogen bond or result in a dipole-dipole interaction or result in a London dispersion force, okay? Now, in terms of the London dispersion forces are the weakest form of intermolecular forces, okay? So let's go ahead and do an example here. So let's take, for example, remember my previous video, I mentioned HCl in terms of a dipole-dipole interaction, but for London dispersion forces, we're going to look at H2, more specifically hydrogen gas, and this is going to be a covalent bond between two hydrogen atoms, okay? Now, hydrogen has an electronegativity of 2.1, and obviously we have another hydrogen atom, so electronegativity of 2.1. So, unlike dipole-dipole interaction, in terms of London dispersion forces, the elements aren't going to have a really big separation of charge. There might be like a little bit of a separation, but definitely not something as huge as we would see in between hydrogen and chlorine or something like that, okay? So because of the fact that there is no separation of charge here, in terms of our hydrogen gas molecule, there isn't going to be one side that is going to be, one side is going to be more positive, one side is going to be more negative, okay? So instead, we just have more like this oval shape going on here. Now, what exactly is London dispersion forces? So you'll see here that we have our H2 molecule here, okay? Now, what I said preview is kind of a little bit of a lie, but in terms of we really don't have a positive side or we don't have a negative side, that's not necessarily true, and here's why. So we end up having, like I said, this kind of like this oval shape with our hydrogen gas, okay? Now, electrons are free-flowing. That means that in our little oval shape, electrons might be on the left side, they might be on the right side, they might be like in the middle. It really keeps on moving. Electrons keep on moving around. There's really no like one place that they're going to end up being. Okay, so electron could be here, and then that being said, based off whether the electrons are on one side or on the other side, could potentially cause our actual oval shape to have a partially negative side on the one side and a partially positive side on another side, okay? This is what's important to understand in terms of London dispersion forces. Now, a London dispersion force is, like I said, the weakest form of the intermolecular forces. So let's take, for example, I think it would be better if we did an example here. So say we have our H2 molecule, and then we have another H2 molecule, okay? Now, like I was saying previously, electrons are free-flowing, okay? Since electrons are free-flowing, we have this oval shape, and again, this oval shape. Since electrons are free-flowing in this case, electrons might orient themselves if there's a neighboring molecule, in this case, another H2 molecule, electrons are going to orient themselves away from the same charge, right? So the electron here, if we had an electron here, then the electrons in this molecule here are going to orient themselves away from that negative charge, right? So they're going to orient themselves over to the right, okay? So now we're actually getting to the kind of this separation of charge again, similar to what we saw to dipole-dipole interactions. We have this partially positive here, partially negative on this side. partially positive again on this side, and partially negative here on this side. So we see here that we're kind of getting that separation of charge again, but even though we don't typically see that when we have an H2 molecule all by itself, okay? This is the reason as to why London dispersion forces are actually also known as induced dipole-dipole interactions, okay? What we're doing is that we're actually inducing when two molecules come together that ordinarily don't have a dipole in their molecule. What ends up happening is that the molecules in an adjacent molecule actually induces a dipole moment onto another molecule, okay, and which causes a separation of charge like we see with our two H2 molecules, okay, and this is so on and so forth as well. So if we have another H2 molecule over on this side, then the electrons are going to orient themselves here, and we end up getting that partially negative, partially positive again, and then so on and so forth. But it isn't just stagnant like this. It keeps on moving around, especially since H2 is going to be a gas. It's going to keep on moving around, and electrons are constantly going to be rearranging themselves. What's important to understand that in terms of molecules that are seen with London dispersion forces, there is no permanent dipole, okay? There is no permanent dipole. There's always a constant flowing and sloshing around of electrons in our molecule overall that doesn't result in a permanent dipole, okay? So like I was saying previously, London dispersions, for that reason, because of the sloshing around of electrons, is not going to be our strongest intermolecular force, okay? Now, like I was saying, there's also videos in terms of hydrogen bonding as well as dipole-dipole interactions. If you have any specific questions for me, then feel free to reach out to me at my personal Chegg account. You can see that I've linked it there on the whiteboard. If not, or if you have any other questions in regards to biology, chemistry, sociology, psychology, or statistics, then you can also send me a message there. Have a great day, guys.